Hello everyone. My name is Hamid Reza Karbasian. I'm a PhD candidate from Department of Mechanical Engineering, Concordia University, Montreal, Canada. Today I'm going to talk about how to simulate the supersonic jet flow and capture oblique shocks. So first of all, we're going to take 3 steps to process this video. First of all, we design a geometry, and after that we build a mesh for the geometry, and after that at the end we're gonna solve the flow in this geometry in Ansys Fluent. The problem descriptions we have is that we have a cross-sectional area at the inlet, throat, and outlet, and we assume that the static pressure at the inlet is 200 kilopascal. So we are going to simulate a jet flow, supersonic jet flow that expands in a tank in order to capture these shock diamonds. So the schematic of problem will be a converging and diverging nozzle. At the left-hand side of this tank, the flow goes into the nozzle from the inlet, and it expands to the tank, and after that you will see the oblique shock. So as you see, the problem is symmetric along the red line. So we can have the domain and just simulate the flow inside of just half of this domain. And in order to reduce the complexity of simulation, and in order to speed up our simulations. And the parameters are given as a dimension of inlet, outlet, throat, and total length of nozzle. And we assume that our nozzle is a 2-dimensional duct with the depth of 1. In another way, if we assume that our cross-sectional area is like a circular one, and it's our nozzle is like a tube, we can change the 2D options in the Fluent into symmetric, but for simplicity we just take it as a 2D duct. And a few things to mention that when you're using a spline, because of a spline's characteristics, it may not give you what you expect. For example, in the converging part of nozzle, just make sure the cross-sectional area is continuously decreasing, and in the converging part, the cross-sectional continuously increasing. And if you don't get a really good result, one of the reasons might be a mesh quality. So before going to the CFD analysis, make sure you have made a good quality mesh. And the thing is that for simplicity of flow, just reduce the complexity and just assume the flow is inviscid without any turbulence. And the thing is that once you start to simulate, you will get a notice as a reverse flow. So reverse flow is a notice, not a warning. And usually for the jet flow, you will get this reverse flow notice in the Fluent. And another thing to mention that when the domain of tank you design for the jet flow, if this domain is not large enough, so you will expect that the residual won't get really small values. So when it doesn't go to really small values, so it means that your domain is small. But for simplicity of this video, we use a really small tank. As you can see, when the jet flow expands in the tank, some large vortices are created along the edge of jet flow, and it makes a circulation. And as we see, if the domain is not large enough, so some part of vortices is in the domain and the other part is out of domain. So because it's a vortex, because it's a vortex, so the flow goes out of domain and again it turns back into the domain. So that's why you will get a reverse flow notice. And it's something normal. It's out of your hand unless you make a really big, large tank. And what you expect to see is that the flow continuously, the Mach number of flow continuously increases from the inlet to the throat, and it reaches 1 at the throat. And in the diverging part, it keeps increasing toward the exit of nozzle, and in the tank, because of pressure difference, you will see the oblique shock occurs. All right, let's get back to the Ansys Fluent. So I launched the benchmark and I'm dragging Fluent to the project schematic. So I'm gonna click on geometry and I'm gonna change it to 2D. And after that, I'm gonna open new design modular geometry. All right, first of all, I'm gonna make it XY plane. I'm gonna click on XY and I'm gonna change the unit to millimeter. Then I go to select polyline and I start to sketch my geometry. All right, and I'm gonna click on closed end. All right. The other thing that I need to add here is some constraint to make these lines perpendicular. So these lines should be perpendicular to each other. All right, this is my constraint. Here you go. The next step, I'm gonna give the dimensions. So the inlet of nozzle, this is on the geometry given, is 140. So I'm gonna click on zoom to fit to have all my sketches here, and I'm gonna say the length of tank is, so I'm gonna select the same length as the length of nozzle for that. So for that, my length of nozzle is 840. I'm gonna give the length of nozzle here. My length of nozzle is also 840. So this one should also be 840. All right. And as you see, this is from this line to this part is my nozzle, and the other part is my tank. So this is the length of exit of nozzle. So I'm gonna give the dimension to that. So I'm gonna say the distance from this point to this point. Oops. Undo. Sorry about that. All right. First, let's make another part of my domain. So I'm gonna say the height of my tank is where is H7? Okay. Is 336. All right. So the other thing is that because I want to make a nozzle, curved nozzle, I have to delete this part. So I'm going to modify, and I'm going to select trim, and I trim this line. All right. Again, I'm going to dimensions. I'm gonna say, all right. And I want to specify the length of these 2 points, the distance of these 2 points. So I think I have to make a line first. All right. And after that, give the dimension. So my length of nozzle will be 168. All right. Now I'm gonna trim this line as well because I don't need it anymore. All right. So for drawing this line, I need a point. I'm gonna add a point here. I will give dimension to this point again. So I'm gonna say the distance from this point to the inlet is 400. And I'm gonna use vertical ruler. So I'm going to say the throat is gonna be is gonna be 105. Here we go. Now I can use a spline to draw my shape. Okay, I'm gonna start from the inlet. I give a little bit of slope. Then I'm gonna connect it to the throat. So as you see, if I change the location, for example, for now, as you see, the cross-sectional area from the inlet decreases first and it increases again. So that's why I said you need also watch the spline to make sure that your cross-sectional area is continuously increasing or decreasing and then increasing. Now I'm gonna connect these lines, perfect, and then open end with fit points. That's it. Now I made my shape. So I have to make a united surface. So I'm gonna select sketch 1 and then I apply it. All right. Then I click on generate. So I save the project. In the desktop nozzle as a project 5. Now, when I want to make a mesh, build a mesh, the challenging part is that to build a structured mesh for this domain. So for simplicity, what I'm gonna do is that I'm gonna split the surface from this line, and then I make a mesh for the nozzle, and then I make a mesh for the tank. So it doesn't make any conflict between the mesh structure between these two parts. So for doing that, I'm gonna go to tool and face split, and then I apply it. All right. And then for the total geometry, I'm gonna select this point and this point. I'm gonna select split from here. All right, and after that, I'm gonna click on generate. All right, so now you can see I have two different faces. So in the next step, I will make a mesh for this area of nozzle, and then I can make a mesh for this part easily. Let me save the project, and then going back to the next step. All right. The geometry is uploaded in the mesh. So first of all, I'm going to click on the method. I'm going to select my domain and then apply it. And after that, I'm going to select edges. And for the inlet and outlet, I will insert sizing. And I'm going to say the number of divisions is 50 points or 50 nodes. For the length of nozzle, I'm gonna insert the sizing again, and I'm gonna select number of divisions, and I'm going to make it 250 points with the hard and a little bit of bias with the bias factor of 5. So let's see. Yeah, that's enough. And here I gave 50 points. I'm gonna give the 50 points for this wall as well, this line. All right. The number of points is 50. Now, the number of points in the right boundary should be the same as summation of this line and this line. So I gave 50 for each of them. So the number of points for this line must be 100. So the reason is that the number of points in the front line or opposite side of each boundary should be the same. Otherwise, our mesh won't be a structured one, and it's gonna be unstructured number of divisions, so it's going to be 100 bit hard. All right. The mesh also for these two lines. So I'm gonna make it 200 points. And after that, I'm gonna check if my mesh is enough or not. Number of points I added. So the next step, I'm gonna add facing mesh, face meshing, and then I'm generate the mesh. All right, it's asked me to select the face first. No selection. All right, this line and also this line. All right, now I'm going to click on generate. All right, as you can see, the number of nodes in the throat has more concentration as we expected. But the thing happens here that there is a little bit discrepancies. The number of the size of grids are a bit large in this area. So what we want to do is that because it's an edge, so the shear layer here is the amount, the value of shear layer here is a bit large, so we need a bit denser mesh in this area. So what I'm gonna do is I'm gonna select again H3, so I'm gonna increase then the concentration of nodes here a little bit more. So what I'm gonna do is I'm gonna say I have a bias with the bias factor of 5. It's a bit a lot, so I think bias of 2 is not bad. All right, and for H1, I'm giving a little bit bias. I'm increasing the number of nodes in this area. So I'm gonna select, I'm going to use the bias with the factor of 2. And then I generate mesh. All right. As you see, I a little bit increased the concentration of nodes in this area. And all domain has, these two parts of our domain has a structured mesh. Now, what I need to do is I have to define the boundary conditions. So I'm gonna select the edge. For this line, I'm gonna add create name selection and I add inlet. This is my nozzle wall, so I'm gonna say wall nozzle. These two lines are my symmetry line. So I'm gonna add symmetry. I can take this part as a pressure outlet, or I can take this line or this boundary as a wall, but I prefer to use it as a wall because it's a ejection of jet flow to the tank. So you either can make it, take it as a wall or pressure outlet. So wall, and these two boundaries are my outlet boundaries. So I'm gonna select it outlet. So the thing is that flow comes from this side, and these two lines, these two boundaries are wall, and it's a symmetry, and it expands in the tank, but it's not the wall of our tank. We assume that our tank is really big one, but we just cut through the tank, and we selected these boundaries, and we give the pressure for these two boundaries as a pressure outlet, and the flow goes out from these two boundaries. All right, let's double check the boundaries. Inlet, nozzle wall, symmetry, wall tank, and outlet. Hopefully it's two wall. Okay. Now the next step, I'm gonna generate again, and then I'm gonna update it. Okay, successfully added to Fluent. Now I'm gonna launch this Ansys setup. And I have a 2D project, and in the options, I'm gonna click on double precision to increase the precision of my calculation. As I said before, here, if your computer has a different number of cores, you can pick a different number here. If you select just one, it uses one core to calculate all the steps, all the variables. But if you go for example, 4, it divides all tasks into 4 different tasks, and it reduces the load of calculation on each core. So the calculation speed increases significantly. So for this case, I'm just using, I'm gonna use 2 core, but if you have a Core i5 or Core i4, Core i7, you can increase to the limit of your computer's core. Then I'm gonna start. All right, I imported the mesh to the Ansys Fluent. First of all, I'm gonna check dimensions. So I have my dimensions here. And as you see, the minimum volume of my mesh is a positive value. As I said before, this value should be a positive. Otherwise, if it's a negative value, it means there is a mesh, or there is a cell in your domain that is skewed, or it's not defined well. So you will have negative volume. And in the physics, we don't have negative volume. So you should change the configuration of your mesh and redesign it. And for the scales, our mesh is the same size that we expected. But if you forgot to change the scale in the geometry design, here you can select either meter, centimeter, or millimeter. Since our flow is compressible flow, we're gonna select a density-based solver. And because we are using the duct flow, we are going to take the planar option. Otherwise, you can select either asymmetric or asymmetric swirl. But for this case, I'm gonna just use a planar, and our flow is steady. Since our flow is compressible, we have to activate energy equation. And then we are going to say our flow is inviscid. Inviscid means there is no friction between molecules of gas, and there is no friction between a wall and gas molecules. So we don't have no slip condition on the wall. And the other thing, for the material, we are using air. But for the air, we have to change the state equation for the density to ideal gas. It's gonna be a good approximate for our simulation. Now I'm going to the boundaries. For the inlet, it's based on the velocity inlet, so I'm gonna change it to pressure inlet. All right. I assume that my stagnation pressure or gauge total pressure or stagnation pressure is 238 kilopascal. And what I realized that the first one is the total pressure or stagnation pressure. The second one, supersonic initial gauge pressure. In the Fluent, it means static pressure. So the first one is stagnation or total pressure. The second one is static pressure. When we have the subsonic flow at the inlet, we don't need to set it any value for that. But once we use pressure inlet and pressure outlet, we can set a value for this one. For example, as I said, the static pressure for our inlet is 200 kilopascal. You can either use or not, but I'm gonna give static pressure and stagnation pressure for this case, and I apply. And for the outlet, it should be pressure outlet. So in order to have a supersonic jet flow at the exit of nozzle, for the gauge pressure or its stagnation pressure, I'm gonna say my stagnation pressure is 50 kilopascal at the end, and the reference backflow pressure, I'm gonna select the total pressure. Then I apply. For the symmetry, the type of boundary condition is symmetry. And for the wall nozzle, it's wall, and it's automatically set it as wall. So I'm not going to change them anymore. Going to method, I'm using explicit raw flux type and second order upwind for the flow discretization. In the control, the current number is 5. We will talk about that later. But for now, I'm going to initialize. So as I said before, you can either use a hybrid initialization or a standard. Once you select standard initialization, you have to start from the inlet. So it says that we have some static pressure here, and this is the velocity of our inlet, and it's almost 0. So I'm gonna put 0 for the y velocity, and our temperature is 290. But here I'm gonna just use a hybrid initialization. Okay. For the calculation, I'm gonna set it to 4,000 iterations. Then I start calculation. All right. As you can see, at the around iteration of 1200, our simulation crashed. So the residual goes to a really large number, 10 raised to power of 12. So it's diverged. So to control these kind of cases, we have to change some settings in order to stabilize our calculations. So one of options for doing that is I'm going to control. So there are some options. I'm not going to change them for now, but we'll go to advanced. So one of things that I can change is the flow, the cycle type for a multi-grid. So I'm going to make either V or W cycle. So I'm going to select W cycle. And other options that I can change, I think that's enough for now. Okay. And in calculations, first of all, let's just initialize it. Now going back to the options in run calculations. And it asks me about the current number. So what I'm saying is that my maximum current number is 1, and the minimum or initial one is 0.1. So it controls the current number or CFL number. So CFL number is a non-dimensional parameter that is related to stability of our schemes or calculations. So what I'm going to say is that change the current number manually, but never exceed 1. And I'm going to change under relaxation from 0.75 to 4. I'm clicking on OK, and I'm using the second order. Now I start to calculate it again. All right, I ran the case until the iteration number of 2000. As you can see, the solution, the solution is stable, and it didn't diverge. But the residual is not really a small value. As I said, one of the reasons could be the size of domain, and the size of domain that I selected, because when the velocity is high, the amount of residual in a small domain, the error accumulates in this small domain, and the boundaries cannot update themselves to the appropriate value. So let's look at the Mach number contour. As you can see, All right. So the velocity increases and it reaches to Mach number 1 at the throat, and after that it starts it keeps increasing in the magnitude of Mach number, and we have a supersonic flow at the exit, and it expands to the tank, and we see the oblique shock. But one of thing is that you see some curves here, which is a result of unsteadiness feature of this simulation. Actually, this simulation is not steady and two-dimensional. So that's why you get some vortices in terms of curves, which means the flow is unsteady. But as we saw in the residual, it's not really low enough. But one other thing that we can consider is the order of accuracy of simulation. The order of accuracy we selected in the method, I think. Let's check. It's a second order upwind. So we can tune it a little bit because when we select the second order, the dispersion in the flow in the domain increases. So if we reduce it to 1, the first order, we add a bit dissipation, and it dissipates the oscillation in the flow field. So what I'm gonna do, I'm gonna use just 50% of order. So the minimum order that I can have is first order, and the maximum in Fluent is second order. So I'm taking something between first order and second order. So I'm using 50%. So it means there is a scheme that takes the discretization to almost something between first order and second order. So I'm gonna run 2000 more iteration, and I will double check the result later and see if I can improve my simulation or not. So I'm gonna start it, and it asks me, do you wanna continue the iterations? I'm gonna say use settings changes for current calculation only, and it starts the rest of calculation with the initial condition of my result I got. So I'm giving this result as my initial condition for rest of calculation. So I'm saying okay. So now it starts for 2000 more iterations. So let's see what will happen. All right, I let the Ansys Fluent to run 2000 more iterations. As you can see, we could reduce the amount of residual for the second part of calculations. Generally speaking, the first order is stable, is much more stable than second order one. So usually, if you feel that your residual is not low enough, or your problem is not stable enough, so you can tend your discretization scheme to the first order. Now let's look at the contour. As you can see, we could stabilize these lines, these curves, and it's currently seems to be much more stable. So the other thing that I want to do, I want to tend more toward the first order, or even I'm gonna use the first order and I'm gonna iterate for 1000 more iteration to see the differences. All right, I'm gonna start, and I give this solution as an initial condition of the rest of solution. All right, and click on OK. So I have to wait. All right, the simulation is done. So as you can see, with reducing the order of accuracy of results for calculation, we could even the residual reduces with more acceleration even faster. So the thing that I have to mention again is that first order scheme is stable, is more stable than second order one, but the accuracy of second order is higher than first order. So you should pick the middle or just first order or second order. It's up to you. If your mesh has a low quality of quality, so if you turn to first order, your error will grows. But if you design your mesh really good, increasing from second order to first, turning from second order to first order doesn't change the result a lot. So let's check out the Mach number again. As you can see, our flow is much more stable, and there is a little bit of bump, but it's negligible. By the way, one thing to mention is that in the boundary condition of outflow, I picked total pressure for my gauge pressure Pascal. But if you assume that your tank, for example, your tank, the pressure of your tank doesn't changing a lot. For example, the stagnation pressure is equal to the static pressure, or in the other words, if the velocity is negligible, you can set the total pressure to static pressure. But here I assume that there is a velocity here and here as well, so that's why I picked the stagnation pressure of 20,000. And I reduce it a little bit because I think the previous number was 50,000. I reduce a little bit in order to make sure we get the oblique shot. All right. One of the important thing I want to show you is that we need to mirror the other part of the solution in order to have a full nozzle. So what I'm going to do is I select view, and I select this icon. As you can see, the symmetry line appears here. If I click on symmetry, it adds one number to a mirrored plane. And if I apply, I will get the other symmetry part. So now this is my full nozzle with the oblique shot at the outlet of converging diverging nozzle. You can also plot different things. For example, if you want to plot XY, for example, you want to plot Mach number or pressure, static pressure along the symmetry line. You can plot it easily, and you can see the pressure. There's a discontinuity between the pressure line, and you can also plot, for example, temperature, and this is the temperature, and you can also try different things. And this is all I wanted to mention for this course, and hope it will be useful for you. Okay, thanks for watching, and good luck.